Hello, this is Sadbir. The topic of our discussion in this video tutorial is the Supremum and Infimum. This is our second video tutorial on this topics. In this topic, I will give you the more details on this concept and I will prove some very important result which we need in this course. So first, let me recall the definition of the least upper bound and also the definition of the greatest lower bound and what is the axiom of completeness. I will begin with the definition of least upper bound. So here is the definition of the least upper bound. So least upper bound is a real number and this real number satisfies the two property. And the first one is S must be an upper bound for A, where A is the subset of real number. And the second property is that it is the smallest upper bound. Or in other words, if you find any other upper bound, if you pick any other upper bound, the S must be less than or is equal to that upper bound. Now I will give you the definition of what is the greatest lower bound, which is going to be very similar to this, just flipping some inequalities. So here is the definition of the greatest lower bound. A real number L is called the greatest lower bound for a for a subset of real number. Number one, if L is the lower bound of A, or in other word, L is the smaller than every element of A. And the second one, this lower bound is the greatest among all the lower bound. Or in any other word, if you find L1 any lower bound for A, then the L is always greater than or is equal to L1. So in short form, we denote the greatest lower bound as the infimum of A, or in short, inf of A. Now I have one more definition which is new for us, which is the maximum. Because sometimes it is a very minor difference between the definition of the maximum and least upper bound, and the student get confused that what was the basically the difference among them. So let me first write down the definition, then I will tell you that what is the major difference between the maximum and the least upper bound. So here is the definition of the maximum. So maximum is also a real number, and that real number satisfies two property. The first property is that this real number must be an upper bound, and this upper bound must be also the member of the set. So the property number one make the difference between the least upper bound and the maximum. Because the least upper bound definition, we are not required that a real number m be the member of the subset A. But here, in order to be a upper bound maximum, that upper bound must be also the member of A. Now, since we have the definition of the least upper bound, greatest lower bound, we can also state the axiom of completeness. So what is the axiom of the completeness? Let's suppose if you have a subset of real number, and that subset satisfy two property. One is it is a non-empty, and the second property is it is a bounded above. So if any subset of a real number satisfy these two property, we can assume, we can state an axiom on this that the sup of that set always exists. So this is our axiom that the sup is always, and that sup will be a real number. So this is our assumption, and that assumption is known as the axiom of completeness. Next, I will give you the picture that how you can basically view the supremum and the infimum on a diagram. So in red, I plot my set on the real line. And now basically first we will plot all the lower bound and the upper bound. So the lower bound of the set will lives on the left hand side of the real line or left hand side of this set. So all the element here on this side will be the lower bound. So this is my lower bound. And the upper bound on the other hand side, they live on the right side of the real line. So these are all my upper bound, which are on the right hand side of my set. And there are going to be the two special bound. One is a lower bound and one is upper bound. So this is the greatest lower bound, and this is called inf of A. Similarly, this bound is the smallest upper bound, and this is what I'm going to call the sup of A. So this is the picture of lower bound, upper bound, and also the infimum and supremum of the set when we plot that set on the real line. Let's now consider some examples and compute their infimum and supremum. So my first example of the set A is, let's suppose I have a set A, which is starting from -3. It is interval starting from -3 and ending at like a 12. So let's suppose this is set. The first I will draw the real line and we plot that set on the real line. Now, as I can see that all the lower bound of my set are here and all the upper of bound my set lives here. All my upper bound of the set lives on the right hand side of the set and all the lower bound of my set lives on the left hand side of the set. So as you can see that now I can basically write down what is the infimum of the set. The infimum of the set in this case, it will be this number, which is the greatest lower bound, and this is a -3. And similarly, I can also define the sup of my set A, which is this number. This is the greatest, the smallest upper bound, which is 12. And here also one thing to notice, because this -3 is also the member of the set. So this -3 is also the minimum of the set. The minimum of the set is also -3. So in this case, the infimum and also the minimum, they are both same. However, the maximum of this set does not exist, because if you say the 12 is the maximum, but it is not the maximum because this is not the part of the set. So maximum of this set does not exist. Let's take one more example. In this case, I'm going to take an example of a set which is a discrete set, n plus 1, where n belong to the set of natural number. So when we have given a discrete set, it is easier to find the sup and info if we write down this set in a list form first. So since I list all the element of this set, and now I can find the list of the upper bound and also the list of it is a lower bound. As you can see that all the member of this set, they are less than 1. So 1 is an upper bound, 2 is an upper bound, 3 is an upper bound, and so on. Even 100 is an upper bound. All the element which is bigger than 1, they are all upper bound. And also intuitively, you can see that any element which is less than 1 is not an upper bound, because that element will become the member of that set. So since that 1 is the smallest upper bound, so we will say the sup of that set is just 1. Is 1/2, 0, -1, and so on. Because 1/2 is the smallest element of the set, and any number which is smaller than 1/2 is also an lower bound. And since the one half is the greatest lower bound, is the largest among all the lower bounds, so the inf of that set A is one half. Let's take one more example. This time my set A is equal to 1 over n minus 1 over m, where n and m both are natural number. Since as I can see again, this is my discrete set. So when I have a discrete set, in order to find the greatest lower bound and uh, the least upper bound, I must basically write the set in a list form. So first I'm going to list all the element of this set. So here I have the list of all the element of this set, and I also can observe that all the element of this set, they are less than 1, and also they are greater than -1. So 1 and -1, they are the upper bounds of upper bound and lower bound respectively. And 1 is the least upper bound because this is the smallest upper bound among them. So the sup of the set A is 1. And similarly, the inf of that set A is a -1 because this is the smallest number, and also this is the greatest lower bound of this set. Here I have one quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. Next, we will prove some important result of infimum and supremum for a subset of real number. Let me first write down the statement of my first theorem. So here is the statement of our theorem. The statement says that if A is a non-empty bounded above set, a subset of real number, then if you have a real number C, and then you can define this new set C plus S, which is defined as adding C in each member of the set A. Then we will prove that the sup of this set, which is a C plus A, the new set, is equal to C plus the sup of the set which was given A. So I will begin. I'm gonna first denote the S as a sup of A, the sup of A. So this implies what I want to show is the sup of this set C plus A is C plus S. So this element is the sup of the set C plus A. So by definition, I need to show, by definition of this sup, I need to show two things. One, I need to show C plus S is an upper bound for C plus A. And the second assumption I need to show C plus S is the smallest upper bound, the smallest upper bound. So this is the definition of the sup. The first I will show that C plus S is an upper bound for A, and the second statement I need to show that C plus S is the smallest upper bound for C plus A for that set. Let's show the first part. Let's prove the first. Since S is equal to the sup of A, so that is given. This implies that S is always larger than or equal to the all member of that set, because this is the definition of the least upper bound, that it is greater than each and every member of this set. If I add C on both sides, I will get C plus X, where for all X belongs to A. So the symbol, the upside down A is a mean for all. Now, what this shows that C plus S is larger than every member C plus X, where X belongs to A, or in other words, it is a larger than every member of this set, which is a C plus A. So this implies, so this shows that C plus S is an upper bound, is an upper bound for C plus A. Because these member belong to C plus X, they are the member of this set. So therefore C plus S is an upper bound for C plus A. So that show our first part. Now the second part, let's prove the second assumption, is the smallest upper bound. So in order to prove that is the smallest, I'm gonna take any upper bound, let U. So in order to prove that C plus A is in a smallest upper bound, I will pick one upper bound, U, which is the arbitrary upper bound. And I want to show that, I want to show that C plus S is always less than is equal to that upper bound. So this is a, I want to show that, but C plus S is always less than or equal to this set. So we want to show that C plus X is always less than or is equal to U, and we will prove this by contradiction. So if possible, assume C plus X is strictly greater than U. So since U is an upper bound, so this is a given that U is an upper bound of this set, and therefore U will be always greater than every member of the set for all X belongs to A. This is the definition of the upper bound, since U is an upper bound. And so this implies U minus C, if I move the C on this side, is greater than X for all member of A, where X is the member of A. So this implies this is an upper bound. So U minus C is greater than every member of this set. And also we know that since uh, S is the least upper bound of the sup of A. So this is a given. So this implies since S is the least upper bound, therefore this upper bound U minus C, this upper bound must be greater than S. So it cannot be basically less than or equal to S, because S is the smallest upper bound and this is just A upper bound. Yeah, so this implies if I move that C on the other side, so U is greater than S plus C, which is in a contradiction because here we assume that C plus S, so I can also write that C plus S is less than U. So this is a contradiction to this fact. So these two things are cannot be true simultaneously. So basically, this C plus S is a less than U, and here we assume C plus S is a greater than U. So this is in a contradiction. So in fact, if this is a contradiction, it means this is not possible. So if it's not possible, this implies C plus S is always less than is equal to U, because C plus S cannot be greater than U. So this implies C plus S is the smallest lower bound, or is the sup of that set C plus A. And in other word, the sup of C plus A is equal to C plus S, or in other words, C plus the sup of A, because S is denoted as the sup of A. So this completes the proof of our first theorem. Next, we will prove an important result on the supremum of a set. Let me first write down the statement of the theorem. So here is the statement of the theorem. The statement says that if you have a real number s, which is an upper bound of a set A, and then that s real number will be supremum if for every choice of epsilon, so if epsilon is given and any choice of epsilon, you can always find a member which is in the set A, so that when you subtract that epsilon from this number s, this is always less than the that member of the set A. So let me draw the picture of this statement, so it will be a bit more clear what the statement is saying. Now the statement says that a real number s, if s is a supremum, if s is a supremum, it means s is somewhere here. So this is the supremum of the set. Let's suppose basically this is the supremum. This is a number s, which is the sup of a. And then epsilon, which is a positive given number, which is a given. If you subtract that epsilon from that s, then this number will be now s minus epsilon. And once you subtract that epsilon, no matter how small is it, you can always find number A, which is belong to the set A. So this is the statement of the theorem. It says that if you subtract a very small, no matter how small positive number epsilon from the supremum, you can always find an element in the set A, so that this element A is now bigger than s minus epsilon. And also this is a if and only if a statement. So this is symbol means if and only if. So this is a bit lazy way to write this statement. Actually, the statement is in two lines. One is if S is the supremum, this condition hold, and if this condition hold, then S is the supremum. So there are the two part of the theorems which we will prove. So the first we will prove the forward direction. In that directions, we will assume S is the supremum, and then we will prove this statement which is on the right hand side. And in the reverse direction, we will assume that the statement on the right hand side is true, and we will prove that S is the supremum. So for the forward directions, what is given? So is given. So first we will write what are the given statement and then what we need to prove. So in this forward direction, the given is S is the supremum, and also is given that S is an upper bound. So F has to be the upper bound if S is the supremum. And we want to show that given any given epsilon positive, there always exist A belongs to A, so that S minus epsilon is less than A. So I wrote a lot of mathematically symbol. So let me give you the name of the symbols, what the notations means. So this means is there exist this symbol means so that, which is a reverse E. So we will start from what is a given. So the given is S is the supremum. So if I, and also the given is epsilon is greater than is equal to 0. So we have a number S, and we have a number epsilon, which is a given now. So therefore S minus epsilon will always be less than is equal to S, because S epsilon is a positive number. So if you subtract the positive number from any number, so that number will be basically less than S. So this will implies that S minus epsilon uh, cannot be upper bound, cannot be an upper bound bound for A. The reason is basically because S is the sup. S is the least upper bound of the set. If S minus epsilon is an upper bound, then it will become also the least upper bound. Because if S minus epsilon is an upper bound, this will implies S minus epsilon is also least upper bound. But we have given that the least upper bound is not S minus epsilon, it is S. So this cannot be true. So this is statement that S minus epsilon cannot be the least upper bound. So if it cannot be the least upper bound, this implies there will exist A, which will be the member of the set A, so that because S minus epsilon is not an upper bound, so we will use the definition of an upper bound. S minus epsilon is will be a less than A. Because the definition of the upper bound, if F is upper bound, if S minus epsilon is an upper bound, this implies S minus epsilon must be greater than or equal to the every member of the set. And now this is the negation. This statement is the negation of that statement. And if the negation of the statement is basically if S minus is not an upper bound, it means there will be at least one element so that S minus epsilon will be strictly less than A. So this is the sort of this statement is the negation of the first statement. So this prove that basically this statement that for any given epsilon, so any given epsilon, we can always find A. So we always find A so that S minus epsilon is less than A. So this proves the forward direction of the theorem. This prove the forward direction of the theorem. Now let's prove the other direction of this theorem, or other word, the converse of this theorem. So conversely, we assume, so we have given, epsilon is given and it is a positive. For every positive number, there exists a member of the set A so that this statement is always true. S minus epsilon always be less than A. So this is given. And what we will show, we want to show that S is equal to the sup of the set. S is the supremum of A. So if we want to prove that S is the supremum of A, that means we need to prove the assertion of the definition of the supremum of a set. So there are two assertions of the definition of the supremum of a set. So we need to prove basically number one, S is an upper bound. And number two, if we have any other upper bound, let's suppose U is uh, any upper bound, we need to show that U that S must be less than U. It means S is always less than is equal to U. So we need to prove these two assertion of this, the definition of the sup of the set, or another word, the least upper bound of the set. We already know in this statement, it is a given that S is an upper bound. So this means this is clear from the statement of the theorem that S is an upper bound. So all we need to prove is we need to prove that if U is any upper bound of the set, then S must be less than or is equal to U. We will show S is always less than or is equal to U if possible, if possible, assume S is strictly greater than U. So we will prove this assertion number 2 by using the method of contradiction. So we need to prove that S is less than is equal to U, and I will assume on the opposite of that, that if possible, S is strictly greater than U. And I will prove that this statement is absurd by giving you some contradictions. So now if S is strictly greater than U, so this means S minus U is a strictly positive number. So I can choose, basically, I can choose because I have a choice now to make of epsilon. So I can choose epsilon S minus U. So I make my choice of the epsilon because epsilon is a given number which is strictly positive. So S minus U is a positive number. So I can choose that my epsilon is this. So now I will use my given statement. My statement says that whenever I have an epsilon, which is strictly positive, there always exist. So there exists A belongs to A so that S minus epsilon is less than A. Now I will plug the values of my epsilon. So this will be a S minus epsilon, which is a S minus U is a strictly less than A. And this will implies S cancel out. So this will be a U is a strictly less than A. But this is the contradiction to the definition of an upper bound because U is, we assume that U is an upper bound. If U is upper bound, it must be less than every, it must be greater than every member of the set A. But here I'm saying that U is an upper bound, but U is also less than A. So this implies this is a contradiction. This is a contradiction to the fact U is an upper bound. So U is an upper bound. So this contradict that fact. So if this is a contradiction, it means this cannot be true, or in other words, this implies S is always less than is equal to U, and this implies S is equal to the sup of A. The sup of A because S satisfy the first property and S is also satisfy the second property of the definition. So this complete the proof of our theorem. So this complete basically the forward and the backward reduction of this theorem. So this is a really important theorems of the supremum and infimum. Whenever we need to prove some number is a supremum of a set, we will basically prove this assertion of the theorem. So you will always say that for any epsilon, we can always find a number A so that S minus epsilon is less than is equal to A. To say that for surety that S is the supremum, which is an also an upper bound of the for the subset of A of the real number. Here I have one more quiz problem for you to practice. Please pause the video for 1 and 2 minutes and work on this problem. This is also the end of this video. Thank you very much for watching. I will see you in the next video.